Controllability of complex networks. So here is the lecture's outline. First of all, we will discuss the complex network, then complex network representation. Then we will discuss the adjacency matrix of a complex network and input matrix. Then we will discuss the state space representation of a complex network and Kalman controllability condition. Finally, we will discuss two examples on this topic. So what are the complex networks? The world today is a world of complex networks where there exist hundreds and thousands of units that contribute together to generate an output. Complex networks include technological networks such as World Wide Web, biological networks such as protein interaction network, and social networks such as Facebook network. Complex network representation. Complex network can be represented with the help of a graph that is a combination of nodes and edges. Nodes represent different identities depending upon the type of the network, whereas the edges represents the link between the nodes. Such as in Facebook network, nodes represents the Facebook users and the edges represents the connection between the users. Here is the general complex network graphical representation. Here you can see node 1 is connected with node 5 and 6 and node 7 is connected with node 6 and 4. Node 4 is connected with node 3 and 2 and node 5 is connected with the node 4. Adjacency matrix of a complex network. Adjacency matrix of a complex network is defined as Aij is equal to 1 if node I is receiving a signal from node j and is equal to 0 if node I is not receiving any signal from node j. Input matrix B belongs to Rn, where n is the total number of nodes in a complex network, and the ith tuple of the vector B or the matrix B is equal to 1 if input is applied to node I and is equal to 0 if no input is applied to node I. State space representation of a complex network. Here is the general state space representation of a linear time invariant system that is given as x dot of t is equal to ax of t plus bu of t. In this particular case of the complex network, A is the adjacency matrix of the complex network, B is the input matrix. X of t are the state variables of the complex network and U of t is the input to the system. Controllability of complex network. In general, controllability is defined as an ability to drive a system from initial to a final stage in finite time. The system is controllable if the controllability matrix C, that is given as follows, is a full rank matrix. So C can be generated by augmenting B, A square B up to A to the power n minus 1 B, where n is the order of the system. So here is an example. We have to find whether this given network where node 1 is giving a signal to node 2 and node 2 is giving a signal to node 3 is controllable through node 1 or not. So first of all, we will generate its adjacency matrix. As we can see that node 1 is not receiving any signal from node 2 or 3, therefore the first row will be equal to 0. Node 2 is receiving a signal from node 1 but not receiving any signal from node 3, therefore the second row will be equal to 1 0 0. The third node is receiving a signal from node 2 but not receiving any signal from node 1, therefore the third row will be equal to 0 1 0. As mentioned in the question, we have to control the network from node 1, therefore B is equal to 1 0 0. As the system has 3 state variables, therefore the order of the system n is equal to 3. Kalman controllability matrix for this particular case is given as C is equal to B augmented by AB and A square B. When we multiply this matrix A with this vector B, we will get AB is equal to 0 1 0 and A square B is equal to 0 0 1. If we augment these three vectors B, AB and A square B, we will get 1 0 0 0 1 0 and 0 0 1. That is the Kalman controllability matrix. So the full rank matrix has the determinant not equal to 0 and in this case C is equal to 1. Therefore this system is controllable through node 1. Here is another example where we have to control the network from node 1 and it contains 4 nodes. So as node 1 is not receiving any signal from node 2, 3 or 4, therefore the first row will be equal to 0. The second row, the second node is receiving signal from node 1, therefore it is equal to 1 0 0. Third node is receiving signal from 1 and 2, therefore it is equal to 1 1 0 0 and fourth node is equal to 1 0 0 0. The vector B will be equal to 1 0 0 0 because we have to control it from node 1 and the order of the system as there are 4 nodes, therefore the order of the system n is equal to 4. We can generate the Kalman controllability matrix C by augmenting B, A square B, and A cube B. We have calculated them by multiplying matrix A with B, A with A itself, and then multiplying it with B, and A with A, and with B at the end, so to generate A cube B. We can generate the Kalman controllability matrix by augmenting these three vectors, and when we calculate the determinant of this matrix, this is equal to C. Therefore, this system is not controllable through node 1.